Okay. Okay.
Grazie.
People on Zoom, sorry for being late. The technical things were slightly complicated. We succeed. Okay. So I'm gonna start from what I said yesterday. Maybe before doing that, since today is gonna be like I'm gonna introduce a lot of notions, some stuff that is quite technical. We just start with like let's say the motivation, the ultimate goal, okay? The motivation for doing all these technical things, ultimate goal. The ultimate goal is to study complex Monge-Ampère MA for Monge-Ampère equations with prescribed singularities. So let me write the question. So we fix capital phi, a theta plurisupermonic function model. I introduced this notion yesterday. I'm gonna recall it. Model. And then we look at the equation theta plus I, maybe DTC, C of phi to the power n equal to f dB, where f is a density with some regularity properties. I'm going to be more precise later on. dB is a volume form, a smooth volume form. Volume form, while the density is not smooth, okay? Not smooth, not necessarily smooth. Theta was the form representing a big homology class. And phi is going to be the solution, and we ask this solution to have the same singularity as capital phi, the potential we started at the beginning. Okay, so this is like the equation we wanna study. So what we wanna do is we wanna prove the existence of such a function, and like we wanna prove also the regularity of this function, right? Meaning we wanna prove that when I look at the difference of these two functions, this is bounded. Okay. So what we did already in all the previous lectures is to define the set of theta plurisupermonic function. We defined what is the Monge-Ampère measures of singular functions. So this was non-pluripolar Monge-Ampère measure. So this is well defined, and this is what we've done like yesterday on Monday. Okay. Why? So let me also say why it's called non-pluripolar. So this is also by my notation theta phi to the power n. So theta phi to the power n is called non-pluripolar. So I already mentioned it, I never wrote it. Non-pluripolar because this measure, this positive measure, because theta phi to the power n does not charge pluripolar sets, meaning that if P is a pluripolar set, So pluripolar, meaning that P is contained in the minus infinity locus of a quasi-plurisupermonic function, 2PSH for quasi-plurisupermonic. Then, so we say that the measure does not charge pluripolar. So if P is pluripolar, the measure does not put mass on P, meaning that when I look at the measure on this set, it's going to be 0. Okay? So the integral over P with respect to this measure is 0. Okay? And this is by construction, the construction I gave to you on Monday. By construction. This is true by construction. Okay, so this is just like this is just to remind you that like the lecture on Monday was to define this guy on the left hand side. Okay, so at least this is well defined. So but then when I started, I said, okay, we start with a model function, a reference function, capital phi, but this has to be quite nice. Meaning, in particular, it has to be a model function. So what we did also yesterday is to define what it means to be model. And model, it means, so phi is model, is a model function. So phi is theta PSH, and is model if phi, capital Phi, has the same singularities of the envelope of phi, where the envelope was this theta plurisupermonic function defined as the increasing limit of the envelope of the minimum in between phi plus c and 0. Yesterday we also saw that this envelope of singularity is equal to a C operator, called the ceiling operator, that is defined as the least singular function having the same mass of phi. Okay? So this is just a name, okay? Ceiling operator is this thing. But anyway, so you don't have to know anything about yesterday to understand this. Okay, so this is the definition of model, and from now on we fix phi to be a model potential, a model theta PSH function. Okay? And what we define, so if phi is model, and also without loss of generality, we can assume that phi is negative, up to subtract a constant, so it's sup equal to 0. And what we define now is like the first energy class. So this is an energy class. So this is x, theta, and capital phi. And this is defined as the as the set of theta plurisupermonic functions such that U is more singular than capital phi, the reference one, and the mass of U is equal to the mass of capital phi. Can you see? Okay, let me do an example. So this is a set of functions, and why this set is gonna be interesting, because actually this is a set of functions with weak regularity. And this is where we are going to look for solution of our complex Moser equation. Okay, so baby case, so in the case when capital phi is equal to d theta, that is model, then E of ex theta capital phi, that is, so it's capital theta, is just denoted by x ex theta, and this set was defined by Gage and Zriai in 2005. While this set here, so this is like it's a real generalization, was defined by in a series of joint papers with my collaborators Tamas, Darvash, and Chingu, so DDL. Okay, so this was like 2018, 19, 20, blah blah blah. Okay, so we have this class, and the point is like the important thing to do. So important. We have to understand this class. This class E. And its relative version, so with the phi, this one. Okay, so we want to understand this space. Why? Again, because this is the space where we're gonna look for solution of the PDE, the nonlinear PDE. It's very similar to what we do in when we want to solve a differential equation. We first solve it like in a Sobolev space with a solution that is has a weak regularity, and then we build up in regularity. Okay, like the same idea. Okay, so we want to understand this class, and now I'm gonna give you a very nice characterization for functions belong in this class, and this is a theorem due to Tamas, Darvash, myself, and Chinlu. I'm gonna first write like in the general statement, and then I'm gonna give at least some of the ideas of some part of the book in a special case. So theorem, this is DDL. So we have that function u is in E of x, theta, and capital phi if and only if p of u p of u is equal to p of u of phi is equal to phi, where this guy here was the increasing limit for C, again, I'm just running again, of the envelope of the minimum in between u plus C and capital phi. And then I have to take the adversarial continuous representation. Okay?
Do you have even local EV example, something which is not in E or in the
yeah, this is okay. Example of something that is not in E. So let's do this case. So examples of things that are in E. Of course, B theta is in E. Or it's theta. This is easy. A function that locally writes as minus log of normal z to the power alpha for alpha in between 0 and 1 is in E as well. So you see that, for example, these two functions have the same mass, but u is more singular than b theta. and something that locally writes as the log of z. This is now in E. Because the motion pair of this guy, this is what we saw like in the other lecture. The motion pair of this guy is 0, so mass is 0.
Ah, okay.
Does this answer?
Thank you.
Okay, and so this is like a very a big characterization. I mean, like an explicit characterization of being in the class E. So being in the class E with respect to something is model potential. It means, so the definition is there. It means that I want to do the envelope of singularity. The envelope of singularity has to be equal to phi. So again, phi is the least singular function having the mass theta phi to the power. Okay, this is the theorem. Moreover, what we also have, so this is one thing, and actually as kind of a consequence, one can prove that, so let's say in the case when capital phi is d theta, then the Leon number of, if I take u, if u is in E of x theta, then the Leon number, if you want, let's write the general statement. So if u is in E of x theta and phi, then one can prove that the Leon number at any point is equal to, for any x in x, the Leon number of u at x is equal to the Leon number of phi at x, where the Leon number of a function is defined as the supremum of all the positive non-negative gamma, such that u of z, so let's take x is going to be identified with 0 in a coordinate chart, and z is going to be the coordinate in u. Then uz is less or equal than gamma times the log plus a constant, and this is on u. Okay. So the Leon number actually, so having a positive Leon numbers, it means that the function it goes a minus infinity in a logarithmic way with this weight. So bigger is the Leon number, more singular is the function. Okay? And the theorem here says that if I'm in the class E, then the Leon numbers are the same. Okay? So just like for just an observation about these Leon numbers, because maybe this is the first time that you see them. Like observational Leon numbers. So we say that if the Leon number at x is equal to gamma that is positive, then u is singular, and in a neighborhood of x, it goes minus infinity as gamma times log, something like this. Okay? But, so having positive Leon numbers means the function is singular. But, having Leon numbers equal to 0 everywhere, in x or everywhere, does not mean that u is bounded. So, for example, if you take u u as before, so minus log to the power alpha, then you can see, you can prove that the log number of u at any point is equal to 0. But the function is singular. Okay? Anyway, so this result, although it says if I'm in the class E, I have more or less, I mean, if I'm the class E, the log numbers of these two functions are the same. So u is going to be more singular than phi, but the log numbers are the same. And then maybe some like an historical notes about this result. Just because here I'm telling you like a story that has more than 50 years, like the later development in the last couple of years. But there was a lot going on. So when theta is equal to omega Keller, phi, capital Phi equal to 0, then this result, so let's say star, let me call it star, star was proved by DiNezza in 2005, and when, so this is the first point, and when theta is just big, and phi is p theta, this the big plus semi-positive, so let's say semi-positive and big. This was proved by Buxom, Estidieu, Gesh, and DiNezza in 2010. So like there is already a big gap. The big case without the semi-positivity condition here was open, and actually this is what we proved with Tamash and Bash in 2017. So theta big phi equal to b theta was proved by DDL in 2017, and this, like in this realization, is more a result of 2020. So really, like there is a lot of contributions of previous authors, of people that were interested in this kind of questions. So this really was one of the open question. It was an open question in pluripotential theory. It was one of the open questions in pluripotential theory, PT. Okay, so okay. So let's say, because I planned to give you like a sketch of the proof of this result, but maybe it's not a good idea. But at least I would like again to observe something over there.
But I think you can have 10 or 15 minutes more because you started later.
Yes, I know.
Okay.
But I don't know if the people want to stay more or do that. But anyway, no, I can observe something, okay? So here, start. So the first easy observation, that we can make is that, so U is in the class E of phi. So by definition, by assumption, U is more singular than capital Phi. So if a function is more singular than capital Phi, then the log number is going to be bigger. So it goes on the inequality is the opposite. So the log number of U is bigger than log number of Phi. Okay? So to prove that they are the same, we have to prove the other inequality. And this is it. So let's try to do that. So what we want is mu of x less or equal than mu y of x. So let's do that in the baby case. I mean baby, not really baby, just like make up our life simpler. Phi equal to b theta. So and then so we are in U, the open subset that is a neighborhood of x. So neighborhood of x, where I want to identify x, the point x with 0. And then here in here we say that theta is equal to the DDC of rho. And rho is going to be very negative. Why not? Up to translation, because we can choose the constant. This is true because locally all the homologies are trivial. So the H11 of u is trivial, and then it means that theta can be written as a DDC of the smooth function. Because theta was a smooth form of rho. Okay? And then I'm saying rho actually rho, there exist infinite rows up to a constant. So rho is unique up to a constant, and I'm choosing a constant in order that rho is very, very, very negative. Okay, so now if we do that, you see that u plus rho is a negative function, because this is very negative, so it's negative, and plurisupermonic in u, right? Why plurisupermonic in u? Because if I take the DDC of u plus rho, this is equal to the DDC of u plus theta, and this is positive because u is theta DSH. Okay? So this is here. Okay, very good. Therefore, so this is now a game. Yes. Therefore, b theta, moreover, let's say, moreover, by the first statement of the theorem, since u is in the class E of x theta p theta, we have that p of u is equal to b theta. Okay? So now we combine all the things together, then we have that b theta plus rho is going to be equal to p of u plus rho, that is again negative, and PSH on u, and this means that this function is going to be less or equal than the supremum yes. So the supremum of all the PSH functions in u negative, such that p is less or equal than gamma log of z plus a constant. Yes, maybe I'm missing something. Maybe I should explain this. So I take rho that is I wanna, sorry, maybe this is what I missed. I wanna prove this inequality with b theta. Then we assume by we wanna do that by contradiction. By contradiction, we assume that if this is gamma, we assume that the Renon number of u theta is strictly bigger than gamma. So the Renon number of u is gamma, and the Renon number of u theta is strictly bigger than gamma.
No.
Come on. This is by contradiction. So this is what we want to prove.
But gamma is more equal. So if you take a contradiction, gamma is larger than. Am I right?
Gamma is larger. Sorry. Right. Thanks. Yeah. Okay. And then we just we do what I say. So we write v theta plus rho that is equal to this envelope, and this guy here is gonna be a candidate here inside. You are locally, so this guy here is PSH. This is gonna be negative because rho is chosen in this way.
And why is it smaller than the gamma log?
Because because the envelope of u has the same Renon number of u.
I'm sorry, but
Yeah.
I'm lost.
Yes.
Isn't this what we are going to do?
Right. Right. Let me see.
And there was a game with the green function.
But this is the green function here. This guy here is the green function
Okay.
of the ball.
Huh?
This is the green. Sorry, this is the green function of u.
Okay.
You can be taken on as a ball. This is the green. Of u. We're going on the other side. Sorry. So we want to prove that. So we want to prove equality. No. Okay. So by contradiction, we are going to assume that the Renon number of theta is strictly less than gamma. Okay. This is true. And we want to find the contradiction.
Okay.
This is true. Then what I said here is true. This is okay. And this gamma log. The envelope of u. No, sorry, Stefano. This is not what we want to prove. We want to prove that the long number. So, yes, sorry. Yes, you're right.
Gamma is by assumption the Renon number of
U.
u.
And now, by contradiction, we are assuming this. Not yet. So the contradiction, like, let me now just sketch you the proof. Okay, this is okay by assumption. So this we are okay with that. So and then if we prove this kind of inequality, so if this is okay as well, then this is by definition again some called the green function of an open subset of Cn, and the green function, so let's call it G. This G of u is known. It was proved already in potential theory that this has the same. This looks like gamma log of z. So if you look at this, we prove that at the end of the story, we would prove that at the end of the story, we will prove that d theta plus rho is less or equal than the green function g of u that has the same singularity. I mean, it looks like gamma log z. This is locally on u. But this means that rho b theta plus rho, so the log number of this at 0, because we are locally where 0 is identified with x on u, the log number of this is greater, because this is more singular than the log number of g of u. But the log number of g of u is 0, since g of u looks like this, is equal to gamma. And this is a contradiction by the fact that the log number of b theta plus a smooth function is nothing else than the log number of b theta. So this would be at the contradiction, because we started with something that the log number strictly less than gamma. Here we have the log number strictly larger or equal to gamma. Hence, contradiction. Okay, so this is the missing point for the moment, but maybe I'm gonna look at this during the break. Okay.
Okay.
So this is the. Do you agree that this is the only thing that is missing? Missing for the moment. Missing point to be proved. And for the rest, one. Okay, but then I also want to make the important observation that in the sense, so this equality also is crucial, and is also like the bridge between b theta and this green function. So, and here we are using the first statement of the theorem. So the characterization of the class E is crucial in order to prove this result on the log numbers. Okay, good.
But then in the group, we didn't actually use the solution of the equation.
The what? The
solution of the equation.
This?
No, we.
But actually, no. If you want, also you can. If you want, you can say, even if you don't say the contradiction, blah blah blah. You do all the thing, and then you end up with the log number of theta greater or equal than gamma. But then we have the other inequality, so we have to have equality if you want. Yes, it's the same. If you like it better, it can be like this. Yeah, maybe. Is that fine? Okay, so my plan now is maybe we can take 5 minutes of break right now,
Okay.
maybe, and then I'm gonna start, so I can tell you what my plan is, to spend the 40-45 minutes to talk about capacity. So I already talked about this notion yesterday, sorry, on Monday. But then I want to spend some time on this to give you, I mean, at least the definition and some of the facts that are going to be crucial for the resolution of the motion coefficient. Okay? So this is really what I want to do. So today is kind of, I mean, it's going to be about the characterization of this class E. It's going to be the set of functions where we are going to look for a solution, and then the notion of capacity that is going to be crucial for the C0 estimate of the equation. So proving that phi minus the model function is non-zero. Okay, do you have questions? No? Okay, so maybe we can rest for 5 minutes, and then I'm going to start again. I think that it's a good moment to stop, no?
Very good.
Ok.
Ma che fate voi? Interrompete la registrazione e poi cominciamo?
Ah,
O no, poi lasciamo così. No, perché poi magari mettiamo questo. No,
secondo me la possiamo lasciare tutta, poi cammino che belle.
Perché ti cerco
Che?
un posto del Politano.
Ah sì, è DDL1, quello per singularity type.
Aspetta. Usa. Quando usa.
E questa.
Database, facile creare database. Questo è proprio che abbiamo un po' di DiNezza. Vediamo quello che fare questo. No, adesso sto cercando su. On the singularity type of what? Ma che tipo sta? Boh.
Posso?
Certo. Allora.
Ah sì, perché
E lì. Sì.
questa roba qui non è questa roba qui,
Sì.
a ogni fissato c'è la stessa soluzione di filo,
Giusto.
quindi lo stesso numero di colonne.
Ok. E quindi?
E quindi quella, per esempio, c'è questa roba qui, lui, sotto C, se tu ci metti le cose, bla bla bla, lui più G è un candidato qua dentro. di vedere il limite da parte dall'altra, ma quando prende da C quasi esce.
Allora, dunque questo
D'accordo che lui cresce verso lui cresce verso di voi, per definizione.
sì, giusto,
Ok. Lui ha la stessa singolarità di lui, non c'è fissato.
perché Phi è più piccolo di Z, insomma di
Quindi più distante di
sì,
altri. Quindi lui c'è lo stesso numero long di Phi. D'accordo?
sì,
Quindi lui più G
sì,
sta qua dentro. Lui è un candidato,
perché
è uguale. Negativa è PSH non vuole.
questa è negativa.
Ma non guarda questo. Lui più G
Lui, questo che
sì, è PSH.
sì,
È
ovviamente,
negativo.
diciamo di sì.
Cioè questo qua è uguale.
Ah, giusto, esatto,
Quindi un candidato qua dentro.
sì,
Adesso tu prendi il limite su C, il limite su C. Quando prende la C lascia questo, il limite su C prendi. Ok? Okay, we start again about this notion of capacity. Capacity. CMD. So the notion of
non la vuoi fare quella?
la faccio?
Beh, è
Ok.
stata a mezzo servizio, non lo
Sì.
so, come fare?
Notion of relative capacity. But before I go back to what I promised, the missing point. So the missing point was written here. The missing point of just before the break. The missing point before the break of the previous proof. The previous proof was to prove that the envelope of U plus G was less or equal than the supremum of all the function PSH of U negative, and we such that E is less or equal than gamma, the norm of Z plus a constant. Okay, so why is that? Okay, G again was such that DDC of G is equal to theta on U, and G very negative, okay, in order to have that P of U plus G is negative as well. So this is a negative function, and also we have the P of U plus G is PSH on U, okay, for what we said. Moreover, just by definition of the envelope, P of U is the limit, the increasing limit of Fc of P of the minimum in between U plus a constant and 0. Okay? And I already told you, observed yesterday that this envelope has the same singularity than U. So it means that the difference is bounded. Okay? So if you are convinced that this is true, if not, you can really ask me for details, any details you want. This implies that the log number of these, so let me call it this UC, okay? As yesterday, I guess. Then the log number of UC at X is equal to the log number of U at X. And this was gamma by assumption. So in particular, this means that UC is the soup of blah blah blah. Yes. So
Smaller
UC
than gamma log.
yes is less or equal than gamma log Z plus something bounded. And this means that also UC plus G is less or equal than the same thing, because G was negative. So UC plus G is less or equal than gamma log plus a constant. UC plus G is negative and UC plus G is PSH on U. So it means that UC plus G is a candidate in the envelope here. Let me call it. What is it? Okay, here. This. Let me call it envelope. Okay, envelope. So UC plus G is less or equal than the envelope. And then you pass to the limit at both sides. Take the limit over C or UC plus G. Less or equal, the limit over C of the envelope is just the envelope, because the envelope does not depend on C. And when you do the limit of UC plus G, you end up with P of U plus G, because the UC, P of U is the increasing limit of the UC. Okay?
Sorry.
Yeah.
Okay, but then I forgot why you really need G.
Because this is the log thing, and this, we are using the previous result saying that this is the green function of the ball of the open subset, and this has the same behavior of gamma log, exactly the same.
Okay.
We are using the log result there. So we are using a log result,
which is that
the green function of the ball looks like gamma log blah blah blah.
Okay.
And then this is why we use G. Sorry, it was ball. Now it became G. Okay. We use the local potential of theta. This is the only reason.
Okay.
Is that okay? No?
Okay. But I don't know nothing about this new one. Okay. But it's obvious that this new of U is an element of, well, this is a supremo of certain things. It's obvious that that supremacy is an element of system. So ensure that you come to
Say it again, because I don't understand. I didn't understand. Say it again.
Mu
Yes.
Is
a number.
A number which
a positive number.
Which is the supremum of the gammas with certain properties.
Exactly.
It's obvious that this supremum is an element of the set of where we are taking to ensure that the inequality.
You're meaning, yeah, it can be proved. It's not clear that the Laurent number of a function, a free supermonic function, is uniformly bounded, so it cannot be plus infinity.
No, he's saying if the supremum is really a maximum.
Yes,
that the sup is a maximum. The sup is a maximum.
But if you take the sup and then you regularize it, you'll satisfy the same assumption. If you do the upper regularization,
Yeah, it solves the same assumption.
Yeah.
Which soup? This soup?
This one, I think.
This one?
I don't know. Which
the supremum of the definition of the number.
It says this.
Yes. That is the supremum of gamma, which satisfies a certain inequality.
And you want to know if the Laurent number, the supremum, is actually a maximum?
Yes.
I think it's true. It should follow from some convexity property of this thing.
The Laurent no, the Laurent numbers are upper semi-continuous. So I guess it's not maximum. Because it can jump.
No, I mean the long number is the soup of the numbers.
The gamma, blah blah blah.
But then you can have the same inequality with the gamma itself. So this is a maximum in a certain sense.
Then you can have
the long number of V, if gamma is the long number of V, then it is true that V is more or equal to gamma log plus of 1.
Yes.
But this is not immediate, I believe, but it follows from, because
I guess
a priori gamma is at the soup of the rho such that V is more than rho log plus of 1.
Yes.
So probably his question is it true that V is more or equal to gamma log plus
Yes,
of 1?
so
I think it is.
I would say yes, but it has to be, there is something to say.
Okay, so the second relation is not trivial.
Which implication?
This one or this one? Ah, okay, yes, exactly. So this is exactly what you're saying. Yes.
That should be verified, but it's,
yes. Yeah, because here the gamma is fixed, and then to be checked. Yes. Okay.
all right, thank you.
We are happy. Thanks to you. So these are much more details to that they are written in the paper. So now we came back to capacity. Also the relative notion of capacity. So but we start with the classic, let's say classical, but I say classical because these notions were developed in 2010 after 2015, and then with Tamash and Chin we generalized everything in very, very general context. So let's start with the general setting. And the classical setting is theta big. And then when you take, so phi is equal to b theta, okay? Our special guy. And what we take a Borel set. So this is now a game, okay? We take a set, a Borel set, and we are going to define the following quantity. So the cap with respect to theta, or B, cap for capacity, defined as the supremum of the motion per measure of theta u to the power n over the set E here, where u is the theta PSH function bounded by d theta minus 1 from below and from above by d theta. So u and b theta have the same singularity in a sense. I'm taking all the functions that are bounded with respect to b theta. And then I take this soup. So like a spoiler alert, the capacity, the capacity, so is a function, so cap is something that is going to take the set of x, Borel set of x, and it's going to give like a positive number, but it is not a measure, because as we are going to see, it's not additive. Okay? So this is what we are going to see in what follows. So this is the notion of capacity. And now I'm going to, this is, even if it's very, very general, I call it baby case, okay? Because later on we are going to replace this b theta with any general model potential to do the relative version. But so now I'm going to list some properties, some also important facts that are not trivial at all, especially some of them, okay? Then I'm going to make a list and also make some comments. So properties. Let's start with a simple one. Properties. So if I have E containing E prime to Borel set, then the cap of E, as you can imagine, also as you can prove, is less or equal than the cap of E prime. capacity of the product. Okay, then other thing, if I look at the capacity of all X, right? This is, what is that? Okay, let's do that, right? This is the supremum of all, of what? Of the integral over X of theta u to the power n, where u has the same singularity, let's say. So u is in between v theta minus 1 and v theta, right? But then this means, so since u and v theta has the same singularities, this means that the mass of u and the mass of v theta are the same. This is the sort of witness from a guy that I mentioned yesterday, and this guy here was the volume of theta, right? It was this homological constant. So this means that the capacity of X is equal to the volume of the capacity of X with respect to theta is the volume of theta. And also at the same, so one can prove that the volume, so let's say the integral over E of theta v theta to the power n is less or equal than the capacity of E with respect to theta. So this, in a sense, is the volume of E with respect to this cohomology class, theta, but this is less or equal than the capacity. Why? Because the capacity is the supremum. And here we are doing the integral over E, so they could be better candidates.
Sorry.
This is over X, so this is the cohomological constant. Okay. Here it's E, and if E is strictly contained in X, there could be like another function u that has the same singularity in v theta, such that the mass on E is larger. This only holds for the entire manifold.
Okay.
Okay. Okay. What else? Something very important. So, like all these properties are kind of trivial in the sense that they follow from the definition, the very definition. And now I'm gonna tell you like something very powerful. That is the comparison of capacities. What does it mean? I mean that I take two forms, θ1 and θ2, such that both define the cohomology classes, and then I want to know if, so I take E, the Borel set in X, and then I want to know if I can compare the capacity with respect to θ1 and the capacity with respect to θ2. Okay? So θ1 and θ2, they don't talk to each other a priori. So can I compare them? Compare these two quantities. So this is the question, and this is actually one of the questions that I looked at during my PhD thesis. And at the time, it was really, I mean, the complete answer to that question was very out of reach. And the statement that I'm gonna give in it's really. In the generalization is due to Chin-Lu, so I made contribution on that, but this data I'm going to give is due to Chin in 2020, 2021, something like this. And then the statement shows that there exist two continuous functions, so positive continuous functions. Such that with f of 0 equal to 3 of 0 equal to 0, such that the capacity with respect to θ2 of E is bounded by f of the function of the capacity with respect to θ1, and the capacity of θ1 of E is bounded by G of capacity of θ2 of E. So we really can compare these capacities. Okay? Moreover, this is like what is going to be very, very important, like, and it's going to be, you are going to understand also the importance in a minute. If cap of t with respect to theta 1 is 0, then also cap with respect to theta 2 is 0, and vice versa.
Okay.
Because of this. Okay, so we can compare capacities. I'm gonna leave the definition for a little while longer, because also I wanna tell you a fact that I think it is important. So two facts. So there are things to be proved. The first one is that pluri-subharmonic functions are quasi-continuous with respect to the capacity, meaning that if meaning that there exists an open set of small capacity such that outside this set the pluri-subharmonic functions are continuous. So I take U theta VSH of theta, then I can ensure that then for any epsilon, I can ensure that there exists an open set of X with small capacity. So you can take any capacity that you want because all the capacity are comparable. This is also like very important. So less than epsilon, such that U is continuous in X minus of epsilon. So this is something actually very, very important. Also like something that we use a lot in pluripotential theory. And the other fact is that one can prove that the capacity of P is 0 if and only if P is pluripolar. So we somehow started with this notion, talking about the motion pair operator, the motion pair measures, and we ended up again with this notion. So again, this second fact is, so, and remember that pluripolar meant that is contained in the minus infinity locus of quasi-pluri-subharmonic functions. And this second statement actually is going to tell me that the notion of capacity is the right notion to work with when we work with the motion pair measure. Because also the motion pair measure was 0 on pluripolar sets. So this measure and the capacity do not charge pluripolar sets. Okay? So this is why, so let me write it down. The notion of capacity is the right one when working with the motion pair measure. Okay, the second, yeah, maybe it's a good thing. I mean, maybe I'm not gonna have time to talk about the relative stuff, but I can do that on Friday. But this is something like a nice example I would like to give you, also to give you an idea of what is this notion of capacity, because the definition is the definition, right? So we have to get a feeling. And the point is that, again, it does not put mass on pluripolar set, but also it does not see big sets. What I'm going to show you is that I am going to take two big sets and the capacity is going to be the same. So it's not true that a setter is bigger than the other, strictly bigger than the other, then the capacity is strictly bigger. So in this sense, it's not a measure. Okay. Do you like the idea? Do you like the plan? I think it's a nice
plan.
No, it's a nice example. Also because maybe you will not believe me, Stefano, but I somehow forgot it. I somehow forgot about this example in preparing the lecture. Ah, this is fine. Okay, so the example, so the claim, let's say, is that the capacity cap does not, so with respect to whatever you want, does not distinguish between these sets. And now for the, I mean, this is very naive, and now you're gonna see what the proof means. But for this, we are gonna take theta equal to omega equal to KLF. And V theta now is 0, as we already said a lot of times. Okay? So also because we said that all the capacities are comparable. Okay, and the examples go like this. So now we take we assume, so this is like an assumption that k times the cohomology class of omega, so k is an integer, positive integer, is equal to the cohomology class of a divisor. So this means this is the Gaussian class of the line bundle associated to the divisor. So it means that the divisor is ample. And then what does it mean, this? Okay, so it means that the two cohomology classes are the same. So it means that there exists phi, a omega per stage function, such that if I do k of omega plus BTC of phi, this is equal to the current of integration along the divisor. So this guy is an element here, and see that since the two cohomology classes are the same, it means that these two guys differs for the DiNezza of a function. This is what I wrote. This is the bar lemma of the very, very beginning. So let me write it down. This means that that 1 over k, so I divide it by k, d minus omega is equal to the DDC of phi. Okay? I mean, it's exactly the same thing, where phi here is a smooth function outside the divisor. Because, and also, actually, so the minus infinity locus of phi is equal to the divisor itself. Because it has to charge it. Why is that, if you want? Because outside the divisor, this is 0, right? So phi has to be smooth outside. And the minus infinity locus is exactly this, d. Okay, so now what we do is to consider, and also, sorry, maybe this I didn't say, we can assume phi to be less or equal than 0. I mean, this is always armless. Yes. Now what we do, we already did that. We already saw this kind of construction. We consider phi j the maximum in between phi and minus j. Remember, it was like the way to construct the motion per measure converging to the one that we wanted. This is again omega p stage, right? And moreover, so in particular, phi 1 is omega p stage and bounded. Right? Because all of these for any fixed j's are bounded. Particularly, I take j equal to 1. So j equal to 1. And then I define Vj. I define Vj the set where phi is less than minus j. So in particular, V1 is the set where phi is less than -1. And then you can see that actually D is contained in V1, right? D, that was the set of the -infinity locus of phi, is contained in V1.
Okay.
Do you read? Okay. So now, almost there. Yes. So now we are almost there. What we do, we say that, okay. So the capacity with respect to omega of x, that is equal to the volume, is equal to the integral over x of omega phi 1 to the power n. Why? Because phi 1 is bounded, right? So the volume is given by any bounded function. Do you agree? Because this is because phi 1 has the same singularity than 0 because it's bounded. Because bounded, okay. Yes, very good. But yes, but what I say here, not here, maybe. But what I want to prove is that omega phi 1 to the power n is equal to 0 in V1. Okay, let's see. Why is that? Why V1 or in x minus V1? Okay, so why is that? Let's try. So we say that omega phi that was omega plus dTc of phi. This is equal to 1 over k times the current integration over d, right? So in x minus v1, sorry, in x minus v1. So in particular, this guy is 0 in x minus v1. Why? Because d is not contained in x minus v1.
D is contained.
It's not contained in x minus v1. D is contained in v1, hence is not contained in its complementary.
Okay.
No?
Yes.
Okay. So it's 0 there, but also in x minus v1, so when phi is greater or equal than -1, omega phi is equal to omega phi 1 in x equal to v1. Phi 1 is equal to 5 here.
Okay.
Because x minus v1 is nothing else than the set where phi is bigger or equal than -1, and here the maximum is phi itself. In this set, in x minus v1, that is equal to the set where phi is bigger or equal than -1, phi 1 and phi are the same function.
Okay. Yes.
Okay, and then I'm saying that this is why omega phi is equal to omega phi 1 in x minus phi 1. Okay, so it means that the motion pair of phi 1 is 0 in x minus phi 1, just because the form itself is 0. Okay, so this is just the way, because I mean, this is like the very details, but the idea is that we are avoiding D, and the current integration outside the divisor is 0. This is the point. Okay, then we are done. because this here, for what we saw from behind, is equal to the integral on V1. And this is less or equal than the capacity, right? Because the capacity was the soup of all this kind of thing. Then look at what we end up. We end up with the capacity of X, that is also the volume of omega, less or equal than the capacity, but also for the first property that we saw, since V1 is contained in X, this is less or equal to the capacity of X, and so we have to have equality. So we proved that the capacity of X is equal to the capacity of V1, even if this set was strictly contained in X. So two different big sets with the same capacity. Is that okay?
Okay.
Okay, I guess this is a right time to stop. And next time I'm gonna recap the properties of capacity, starting directly with the relative fraction. Okay. Thanks, Stefano.
Thank you.
People on Zoom, if you have questions, I'm happy to answer. Even if you wanna write me questions by email, I can answer like in direct next time at the beginning of the lecture. Yes, Armando.
No, it's all okay. Don't worry.
Yeah, for the moment, I don't have any serious questions. Thank you.
Ciao, guys.
Bye.
Bye. Stefano, puoi interrompere quando vuoi.
Ciao, ciao.
Ciao.
Ciao, ciao, ciao.
Guarda, questo esempio è divertente.
Sì, carino.
Did you get the example? Or there is something missing?
No,
It's okay. I mean, it's a nice example also because it's very explicit, and in this way you really understand that you don't see capacity, and the motion per measure don't see this kind of thing. Vabbè. Io adesso sono distrutta. Che disperata. Non ti sei ancora...
Com'è?
Hai finito di registrare? Dai.
Sì, sì, mi sono scollegato. Ciao.
Ciao!
Scusa un attimo, no,
No, come ti sei scollegato? No, mi devo abbandonare io.
che mi sono...
Vai, parli.